Okay, welcome back. Today we're going to continue chapter 5. We're taking a look at section 5.2, inverse functions. So the idea of an inverse function is that we would like to have a function that undoes what another function has done. So for example, if I take f of g of x, I start with x, I go through g to get to g of x, f is going to undo what g has done. So f will take me back to x. From a different perspective, if I were to start over here with x and then follow f to f of x, then g would also undo f of x, bringing me back to the original. So it doesn't matter which side we start on, which side we call x, passing through one function and then passing through the other function will get me back to the original, and it doesn't matter which one I start with. As long as I do one function and then the other, I'll reset. The notation will be a -1, kind of like an exponent on the number, but it's not actually an exponent because we know a -1 exponent would feel like division, and this isn't really division. Inverses are not division, it's undoing. Division undoes multiplication, so if the function is not multiplication, then we're not going to end up having an inverse here being represented as division. No, that -1 input is meant to mean that we are undoing what the original function has done. If a function has an inverse, and not all functions do, then we would say that it is an invertible function. Now, there's a couple of very nice properties that inverse functions have. First of all, the output of one function would be the input of another. The output of a function would be the input of its inverse, and vice versa, which means that the range of a function is the domain of its inverse, and vice versa. The next one, f of a is equal to b, if and only if f inverse of b is equal to a. This makes sense. If I plug a into f and get b, then plugging b into the inverse should get me back the original, which was a. Now, the next property is very cool to see what an inverse would look like on a graph. So let's go ahead and make up a function f for a moment. Let's say that this is my function f. In terms of the inverse, I can obtain it by reflecting across the line y equals x, which means that I will have something that looks like this. So if the top function was the original f of x, the bottom function would be the inverse, f inverse of x. They are mirror reflections of each other across the diagonal line y equals x. And we see for each point on the graph, if this was the point A, comma B, then on the mirror graph, the same point would show up reflected with B, comma A. Finally, inverses are unique. Every function only has one inverse. This makes a lot of sense if you think about the way the graphs work. There's only one way you can reflect across this line. And there's only one way that you can undo something. You can't undo it in two different ways. You would have to either get the same thing, which means there's only one way to do it, or you would get two different things, which means you're not really undoing in the first place. The inverse is unique. There's only one inverse. Now, the question then arises, how can I tell if a function has an inverse? And there's a couple of ways. The first way we're going to look at is this idea of one-to-one. So one-to-one means that if f of a is equal to f of b, then a is equal to b. Well, what does this mean? Let's take a look at a specific example of something that is not one-to-one in order to see the idea. So if I was to take a look at a graph we're fairly familiar with, y is equal to x squared. We know that this graph will have the point 2, 4, and also -2, 4. Now, this is not a problem for being a function. It's perfectly fine that two different x values give the same y value. But that means that the function is not one-to-one. Because in this case, f of -2 is equal to f of 2. Both sides are 4. But -2 is not equal to 2. Two different inputs gave me the same output. That means my function is not one-to-one. A one-to-one function would never have this happen. Now, thinking visually what this looks like, two different x values with the same y value are horizontally across from each other. That means that graphically, I can know whether a function will be one-to-one with something called the horizontal line test. It's very similar to the vertical line test. We'll use a horizontal line. So in this case, I have a horizontal line that passes through this function in two different places. It is not one-to-one, and it is not invertible. Because the idea is that, well, if this is 2, 4, and this is -2, 4, well, what would f inverse of 4 be? Is it 2? Is it -2? Is it both? Is it neither? None of those seem like the best option. We can't possibly take the inverse. And if I was to go ahead and graph f inverse, so let's say that this was f. If I tried to go ahead and graph f inverse, well, the inverse would be reflected, which would look like this. And now I failed the vertical line test. Not a function. If we're not a function, then we can't possibly have an inverse. So if when you reflect it, you would fail the vertical line test, you're not invertible. And if reflection failing the vertical line test, that means the original would fail the horizontal line test. An example of a function that would work would be something a little bit like this. In this case, every single horizontal line I can think of is perfectly good. Each one only crosses through my function once. It's okay that there are some horizontal lines at the bottom that don't pass through the function at all. It just has to pass through the function either once or never. If this was my original function f, then the graph of f inverse would look like this. And that appears to be a function. No issues with the vertical line test. We'll summarize all of this in a theorem about invertible. In this case, the following are equivalent. Either f has an inverse, and it is one-to-one, and it passes the horizontal line test, or none of those things are true. It's either all together or not at all. Basically, this means that if I want to check if f has an inverse, if it's invertible, then I can either check if it's one-to-one, or I can check if it passes the horizontal line test. Typically, if we have a graph, the horizontal line test will be very quick to see, but it's not always easy or practical to get a graph. So we'll want to make sure that we're able to do the other methods as well. So let's go through a couple of examples here. So to determine if f is invertible, we have two approaches. Approach number one is to check if it's one-to-one. If it's one-to-one, that means that two different outputs, or excuse me, if I get the same output twice, I would have had to have the same input each time. So let's figure out if that ends up being the case. Let's suppose that a over 1 minus 3a was equal to b over 1 minus 3b. That means that I have A and B both being plugged into this function and getting the same output. We want to figure out if A and B would be the same. So I would start by cross multiplying. A times 1 minus 3B is equal to B times 1 minus 3A. That would give me A minus 3AB is equal to B minus 3BA. And of course, I can cancel out the 3AB and the 3BA. Multiplication, the order doesn't matter, which simply gives me A is equal to B. That means that the two inputs were originally the same, so the function is invertible. The other approach is to simply find the inverse straight up. And here's what you do. Start with the original function. Y is equal to x over 1 minus 3x. And then immediately switch x and y. Your goal is going to be to solve for y. So I'm going to go ahead and multiply 1 minus 3y times x is equal to y. And then I'm going to go ahead and factor, not factor. I'm going to distribute. So that'll give me x minus 3xy is equal to y. Then I'm going to say x is equal to 3xy plus y. And now I am going to factor, because I would like to get y by itself. So I can pull out this 3x plus 1, leaving me with y behind. And thus y is equal to x over 3x plus 1. Every single thing that I did here was allowed to do, and I'm getting out a single function. Therefore, we are invertible, and this is the inverse. F inverse of x is equal to x over 3x plus 1. Let's try the same thing with one other function, x squared minus 10x. Now, we know that this function will be a parabola, which will immediately fail the horizontal line test. So if we have a graph here, we know that it's not going to be one-to-one, and it's not going to be invertible. But let's show how we would show this if we were going to do this out by hand. So first, we can check if the function is one-to-one. A squared minus 10a is equal to b squared minus 10b. We would need to show that there is several different answers that would end up working. Now, there's two ways that we could go about doing this. Way number one is working with the equation and doing some algebra. Way number two is just finding a specific point. So for example, if I were to here take this function and factor it, I would have x times x minus 10 is equal to 0, which means x would be 0 or 10. So if a is equal to 0 and b is equal to 10, then 0 squared minus 10 times 0 is equal to 0, and also 10 squared minus 10 times 10 is equal to 0. That's two different inputs with the same output. Therefore, this function, it's not one-to-one. We can alternatively try to find an inverse here. Y is equal to x squared minus 10x, which means that x is equal to y squared minus 10y. Immediately I see an issue, because if I was going to try to solve for y here, what I would need to end up doing is completing the square. That would give me x plus 25 is equal to y squared minus 10y plus 25, which would be y minus 5 squared. But then I have a problem, because when I am solving for y, I just took a square root, which means I need a plus or minus. And that is not allowed in a function. Because I've got this plus or minus, I've now got these two different outputs. So because I took a square root, this will not end up working. No matter which way I think about it, the horizontal line test, two different inputs giving me the same output, or the actual algebra of finding the inverse, three different ways of realizing that it is not invertible. Okay, that's all we have for today. See you guys next time.